chapter 10 is about homomorphisms instead of isomorphisms. A function phi from G to G bar is a homomorphism if it's operation preserving. Phi of AB equals phi of A times phi of B for all A, B, and G. And that's it. Nothing about being one-to-one, nothing about being onto. Isomorphisms are homomorphisms. If it is one-to-one and onto, it's still operation preserving, so it's still a homomorphism. But if you've got an operation preserving function that's not one-to-one and or not onto, as long as it's operation preserving, it's a homomorphism. We've emphasized linear algebra applications from time to time. That applies here. Any linear transformation between any two vector spaces is a group homomorphism. Example, if G equals V and G bar equals W, where V and W are vector spaces, and if phi from, well, I'll go ahead and use the V and W, from V to W is a linear transformation, then phi is a group homomorphism. Okay, that's a long-winded way of saying linear transformations are group homomorphisms. Why? First of all, remember vector spaces are groups under addition. Not under multiplication, nothing about multiplying by scalars. We're not thinking about scalar multiplication of vectors. Nothing about dot products. Nothing about cross products. Okay, we're just thinking about adding vectors here. And a linear transformation does satisfy, let's write it this way, this kind of property. With addition being the operation, this is operation preserving. Linear transformations also preserve scalar multiplication, but we don't have to think about that here. This is good enough. In particular, if V and W are, say, Rn and Rm, this works. If V is, say, Rn and W is Rm, n-dimensional space and m-dimensional space with coordinates that are real numbers, this works. And phi would be represented by matrix multiplication. Say phi of V is A times V, so for some matrix A, where A would be m by n. That's a prominent example of a group homomorphism, linear transformations. And this also leads to the next big topic in a natural way. What did you do with linear transformations in linear algebra? You often found their kernel. Remember kernel? Give you nightmares? What's the kernel of phi? Let's go back to the general case here. Say phi goes from G to G bar. What's the kernel of phi? It's the set of everything in the domain that gets mapped to the identity in the codomain. For a linear transformation between vector spaces, the kernel was every vector in the domain that got mapped to 0, the 0 vector. In the codomain, this would be in W. the solution set. In the Rn and Rm case, the solution set of a homogeneous system of linear equations. Kernels were solution sets like that, which even if M and N were the same, for example, even if you're going from R3 to R3, it's possible the kernel could be non-trivial. Oh, more memories. For example, this is always kind of fun to me. If you create the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, and do row reduction, RREF, you get a matrix, you get a row of zeros, which means if you had the corresponding homogeneous system with the column of zeros on the right, there'd be a free variable. X3 would be a free variable. X1 and X2 could be written in terms of the free variable X3. The kernel would be non-trivial is what I'm trying to say. And I don't know if you remember, that was enough in linear algebra to say the linear transformation was not one-to-one when the kernel is non-trivial, and that's true with group homomorphisms as well in general, and their kernels. If the kernel is non-trivial, if it contains more than E, then phi will be not one-to-one. And if it is trivial, if it is just E, then phi will be one-to-one. So in general, kernels of group homomorphisms tell you whether the group homomorphism is one-to-one or not. It is a subgroup of G, and in fact, it's a normal subgroup of G. Oh, I often put that on tests. Prove that's a normal subgroup. What's the idea of that? I won't do a full proof, but what's the idea? Use the normal subgroup test. To prove this, I'd want to show that A cur phi A inverse is a subset of the kernel for all A in G. That's an A inverse there. Right, that's the normal subgroup test. Usually this is an H. So how do you do that? What's the idea? Give me an arbitrary thing in here. Is it in the kernel? Phi times A to X A inverse, where X is assumed to be in the kernel. What does this equal? Use the operation preserving property. And use the fact that we're assuming X is in the kernel. So phi of X is E bar. And then this does simplify to E bar. That basically does it. So kernels are normal subgroups. So you can form the factor group. Which brings us to our last 5 minutes of class, where we emphasize a very, very important theorem with an important sounding name, something called the First Isomorphism Theorem. And I do feel like talking like that way every time I say it. First Isomorphism Theorem. What does the first isomorphism theorem? Sounds like an important theorem. It is. First isomorphism theorem is, you could call it the main topic of chapter 10. Well, the other main topic is just what is a homomorphism in the first place, and what is a kernel, and kernels are normal subgroups like we just talked about. If phi from G to G bar is a group homomorphism, so it's operation preserving, then the factor group of G by the kernel of phi, which you can form even if G is not abelian, G could be any group, because kernels are always normal, is isomorphic. Well, You'd like it to be isomorphic to G bar, but that's only the case if phi happens to be onto as well. In general, it's isomorphic to the direct image of G under phi, which will equal G bar if phi is onto. This equals G bar if phi is also onto. But in general, it may not be onto, and so it may not be equal to G bar. First isomorphism theorem's got lots of applications for classification of groups and helps us see lots of facts about what certain groups are isomorphic to. And for example, one thing it can help us prove is that the factor group of Z by the kernel, by the cyclic subgroup generated by N is isomorphic to Zn, like I mentioned at the beginning of class today. Here's an example. How would you prove this? You'd want to use the first isomorphism theorem. How? I guess I've got to come up with phi that maps Z onto Zn and has a kernel equal to that. Say that again. To apply this first isomorphism to show this, think about it. Evidently, I'd have to come up with a phi, a group homomorphism from Z to Zn onto Zn, if I'm going to get equality here, with that thing, that cyclic subgroup of Z as the kernel. Why? Let phi be a function from Z to Zn defined by mapping an arbitrary number m to what? To something in Zn. How can I guarantee that if I take an arbitrary integer m, I'm going to get something in Zn? Mod by n? Yeah, that's what you do. M mod n. We've actually talked about this kind of thing before. That's the natural thing to do. And it's onto, right? For example, if n were 10, if we're talking about Z10 here, the elements that get mapped onto all those elements from 0 to 9 would be the numbers from 0 to 9 and more. Each element over here is going to have infinitely many things that map to it. You need to prove this is operation preserving. You would need to prove phi is operation preserving, but that's pretty easy if you use properties of modular arithmetic back in chapter 0. And what's the kernel of phi? It's everything that gets mapped to the identity, 0. What numbers get mapped to 0? 0 does, n does, 2n does, 3n does, 4n does, negative n, negative 2n, negative 3n. The kernel is pretty clearly the cyclic subgroup generated by n because we're modding by n. That does it. That's essentially the proof. And as long as you prove it's OP, but again, that's based on properties of modular arithmetic. Yeah, that's kind of interesting. And you could say important to realize that any group like this is really cyclic and it's in fact isomorphic to Zn. In fact, this is a common way of defining Zn in the first place.